Welcome to today's tutorial, and we're going to be looking today at FIFO buffers again. Now, a FIFO buffer is a first in, first out buffer. Sometimes it's called a circular buffer or a ring buffer. And today we're going to be looking at three different examples, one set up for buttons, one for sensors, and the final one will be for processing some interrupt timings. So moving over to the webcam, this is the setup I have today. I'm going to be using an Uno for this example. Then what we have here are obviously 4 LEDs, 330 ohm resistors. Then I've got 4 buttons. Each of them are using a pull down resistor. I think these are 4.7K, something like that. I've got the LEDs going into pins 12 down to 9, and I've got the buttons going in pins 7 down to 4. So let's have a look at, if you like, how the FIFO buffer is going to work. So what I'm going to do is just press the buttons in a random order, and what I want you to notice is how the LEDs then output. So I'm going to press, there we go, a random order of buttons, and you'll notice now that the LEDs are mimicking the order that I press the buttons in, but obviously they're doing it at a much slower rate, as we'll see in the code. So going over to the Digital Town site, obviously I've done a backup page for this. I've already done one tutorial on the basics of using a FIFO buffer, but just a quick recap of how the buffer works. We have an array with a number of elements. The number of elements I will be using today is 256. Watch the first video if you want to know why I picked that number. Then we have 2 other variables. One is giving us the write position, so the position that we're going to write our next piece of information to. Then we have the read position as a separate variable. And what happens is, as we put our information in, we then have a separate system that, if you like, is working through that information in the same order and doing our processing, whatever we want to do, based on what it finds in the buffer. And of course, the read is always trying to catch up with the write. So let's have a look at our code and we'll see how it works. Now, our first example today is this one, FIFO buttons LEDs version 1. That obviously is the item I have on the desktop right now. So we have a variable, the read position, which is a byte. The reason I've chosen a byte is that the buffer I'm using is 256 elements in size. So I can use a value between 0 and 255, which is nicely fitting inside a byte. Then obviously I've got the same for the write position. I've got my buttons in an array. Rather than setting them up separately, I've set the pins in the array. So if you like, this button array now holds the pin numbers 7, 6, 5, and 4. For the buttons, I've got a debounce set. Now I've got mine set at 350 milliseconds because I'm getting old and slow on the buttons. If you're a bit quicker on the buttons, you probably want this at about 250 milliseconds. And then I've got an unsigned long that is going to store my debounce timer value. I've then got an array for the LEDs. Again, these are the pins 12, 11, 10, and 9. Those are just stored in that integer array. Anyone who's seen my examples before will know that current millis is going to store the current time of the board in milliseconds, and read millis is another timer that I'm going to use because I'm going to be using time as the trigger to read from the FIFO buffer. Coming down to the setup that we have here, very simple setup. I declare a variable q that I store as an integer. I've then started the serial monitor and printed out the name of the sketch. And then I've set my buttons all as inputs and my LEDs as outputs by basically working through the array in this for statement. Right, dropping down to the main loop, I declare my integer again q because I'm working through the elements of my array using q. If you're wondering why I call that variable q, it's because it's top left on my keyboard, and just using a single letter means that I don't misspell it. It's as simple as that. The next thing, you'll see this in a lot of the sketches I do, I start the main loop by storing the value of millis in this variable current millis, because that means I can use this variable in a number of timers. So that's what that little section does. Now the next section, this is where we are storing the button presses if they occur. So we have an if statement around the outside of this. This is this current millis minus debounce millis is greater or equal to the debounce timer. This is just a debouncer for the buttons, because if I didn't have this in, if I press the button, it's going to read multiple button presses. So the first thing we want to make sure is it more than, in my case, 350 milliseconds since the last button was pressed. I've debounced them all together because there's no way I can move between the buttons any quicker than that anyway. Then I'm going to work through my buttons. Now, because I've got their pin numbers in the button array, I can literally do a digital read on each pin one at a time. At this point, if a value, if the digital read, because I'm using a pull down resistor, so if the button is pressed, this value here is going to be greater than 0, it's going to go to 1. At that point, I know a button's been pressed, so I'm going to set the debounce timer. That's only set if the button has been pressed. Otherwise, I want this to trigger constantly so that it's always ready for the next button press. Now, once we've updated the debounce, the next thing is to store the value of Q in the Fifo buffer. So it takes the value of Q and it writes it to the Fifo buffer in the current right position. Now, if you remember when we looked at this sort of example, it's now, if you like, it's going, okay, this is the next position I'm going to write to. Once it's written to that position, we increment the right buffer as the right variable, as we'll see here, and then it's ready for the next right position. Now, I'm also serial printing the fact that the button, if you like, has been pressed and the value of Q. That's just to sort of give you some visual guide as to what is happening. Obviously, if you were doing this in some production code, you'd take the serial prints out. So at this point in our code, if you like, we are now fulfilling the left-hand side of this diagram in that we're now storing our values in our list, if you like, our Fifo buffer, our to-do list. The information is being stored there. Now we need to get round to reading the data back out. So moving down the main loop, I've then got this second section that is dealing with the read side. So now we're going to be reading out our information from the buffer. Now, because I wasn't willing to come up with any sort of fancy processing code, I am just using time. So what is going to happen is I've got this timer that I've set up. Again, I'm using the value of current millis, and I've got a read timer. Now, if I was doing this for something in a project, basically in the main loop, I'd probably be processing this as quickly as possible. But the reason I've done it this way is so that you can have a visual demonstration that, if you like, the output is in the same order as the input. So the first thing it now does is it says, is the read position not equal to the write position? So coming back to our diagram, what it's saying is, has the read caught up with write? If these were at the same value, then there's nothing more to be processed because the read has processed everything up to the write variable. However, if there is a difference, if these are not equal, then there is something to be done. So we then start to process the next item in the FIFO button. So what I've done here as my processing, the first thing I'm going to do is just serial print the item out. And then I've gone through my array of LEDs and I've turned them all off. Very simple bit of code. I've turned them all off, and then I'm going to turn on the one LED that is equal in the, if you like, that has been set up in the FIFO buffer from our buttons. The way this is working, if we go to the web camera, if I press this button here, that's obviously to trigger the first LED, second button, second LED, etc. Now skipping down to the bottom of this sort of loop, I've then updated the read position, and then I've just printed out some information that's showing me has the read position caught up with the write position. Obviously in production code you wouldn't do this, but I'm just doing it as a visual example of what is happening. Now the code that I've written is very simple because we're just doing some LEDs. What I've done as well in the code, I'm just going to uncomment this to make it a bit clearer. I've put a switch statement in. So this would replace, if you like, this bit of code here, because obviously this is very simple. We're just processing some LEDs. Imagine now we're doing something a little bit more complicated. So we've got the value that has been stored in our FIFO array. So if it was Q was 0 when it got stored, when we come to process 0, in this case, once again, I'm just going to turn the LED on. As far I'm turning all the LEDs off first, but I'm just going to turn on the one LED that is the value of the FIFO read position, which is this item we're doing the switch statement on. Then obviously for case 1, this could be triggering a relay, 2 could be a servo, this could be a stepper motor, it could be a combination of whatever. But if you like, your processing code would run here, and that's why normally you wouldn't be using a sort of a time element. You would run through this switch statement, do whatever you've got to do, and then run round and say, okay, what's the next item to be processed? So if you're using a non-time version, these lines get taken out, and obviously the one end bracket gets taken out, and your processing will look like the switch statement. So we've got the webcam now and the serial monitor. So I'm going to press some buttons as quickly as I can. I'm going to try and get quite a few in the buffer. There we go. And as we now look over here, you can see where I'm pressing the button. And then we've got my read position, and you see here that read position 1. So if that, like that read position, that read value, hang on, we're scrolling there. Let's stop the scrolling. You can see the first button I pressed was 1. And now we're reading button 1, and our read position in the array has now moved up to 1, but our write position is at 4, and that's because we've now written position 0, position 1, 2, 3. So write is waiting for 4, read is at 1. I then add some more buttons. Now at this point we've now read to position 2, but I'm now up to write position 7, and so on and so on. And so it works its way down. Now, as soon as I stopped pressing the buttons, obviously it slowly catches up with the read and write positions until it finally stops. Let's just bring this up so that you can see it. right at the bottom, we have this value where the read and the write position are the same. Just going to enable the system again, and let's press some more buttons. There we go. So I've pressed some more buttons, and as you can see, the read and the write positions now become unequal, and once again we're slowly processing through the system. So that is basically how this FIFO button buffer is working. Items are being processed, they're, if you like, being placed in the buffer, and then I'm slowly working through, if you like, that to-do list with the read positions. Now for this second example, I'm going to do a setup as if I was using sensors. This is slightly different to buttons, as you'll see, and just requires some small tweaking of the code. If you like, the inputs and the outputs are going to be the same, but we're just going to have to process them slightly differently. So I've written in here, so this is a model railway example. And I want you to visualize, we have 4 railway tracks, and trains are coming into these areas, and then there is one track that leads out of this area. So what we're trying to do is say we want the train that arrives first to be the first that leaves, and then work through that system. But of course we don't know which order the trains are going to arrive in. Now the sensors that are being used for this are reed switches. So a reed switch is usually triggered by a magnet. Now they work in a very similar way to a button. So I've actually had to put a very small debounce in on the system, because if you like, as the contact is made, it could make and break. It might bounce as the contact is made. So you'd get multiple, if you like, on-off positions. So we only want a single sort of on when the switch is triggered. So therefore we still have a small debounce, but much smaller than we would for normal buttons. However, the other thing that we need to think about is, imagine our train has come in on this track, and now there is another train waiting on this track. So now both tracks are full. While a train maybe from down here is leaving down this track, that's not going to happen in a fraction of a second. That is going to take a period of time. So during that time, this train is going to be constantly sat over its sensor, which in our case is a reed switch, which is going to be constantly saying, you know, it's gone high. Now, if we just processed it as we process the buttons, that would mean that this sensor here would keep adding LEDs, if you like, in the queue to be processed, when actually we only want the train to be processed once. So this time we're going to have to record the state of the pins, as I will show you. So the main change, if you like, in our variables is I have added a new variable called button state. Now I've added it as a separate array. I'll be honest, normally if I was doing it for myself, I would have changed this array and made it a 2-dimensional array. However, I know some people struggle with arrays, and especially when we start to get to 2- and 3-dimensional arrays. So I've just left it as 2 separate arrays to keep it simple at the moment. However, the button state will be storing the state of these buttons, if you like, the state of these pins. So working down through our sketch, the setup is exactly the same. When we come to the main loop, just to keep it easy, the outputs, the way the LEDs are lit, I have also kept exactly the same. Let's just comment that out, because otherwise that's going to cause some issues. Right. Let's have a look at the bit that is different, and that is to do with our button reading system. So in our previous sketch, we were using the timer, but this line of code was within the button read statement. So we had done our digital read, and then if a button was pressed, then we changed the debounce value. And that is the way, if you like, that a normal button debounce would work. However, this time we're not reading buttons, we're reading sensors. And so by putting this line here, it means that all the sensors are now going to be read at an interval of our debounce timer. Now for this sketch, I have changed that value to 20 milliseconds. So all of these sensors are all going to be read every 20 milliseconds. And that's going to happen constantly. Now, thinking back to our sensors, as we saw earlier, the train can now be sitting on top of our sensor. So our sensor has gone high. So let's start to think about how this works. So we're going to do our read of the sensor. If it's gone high, we're going to process it here. If the button is low, we're going to update the value in the button state array to 0. And we're always going to do that. We just don't care. We want that back to 0 so that it's instantly ready to be triggered again. However, when we look at this system here, before, if we just said, okay, when the button is high, we're going to add our item into the Fifo button. The problem is with the train sat over the sensor, it's going to be putting endless values into the Fifo button buffer. In fact, with our current system, it's going to put one in every 20 milliseconds. That is not going to be good. So what we're now saying is we've got the value of the digital read, and then we're saying if the current state of the button is not equal to 1. So imagine no train has triggered this sensor. Now a train is parked on top of the sensor, and all of a sudden the sensor goes high. So what we're saying is the old value was 0, so it's not equal to the new value, which is 1, in which case we're going to set the state of the button to high, and we're going to put that information into the Fifo buffer. However, if the button is already being pressed, in which case the button state will already be 1, then we don't actually want to do anything. So that will be the same train sitting on top of the same sensor with the same information coming in, and we really don't care about that. We don't want to put any more values into our system until the button state has gone low and, if you like, the next train has come in. Now this one's going to be a little bit more difficult to visualize. Imagine my train has come in here on this track. I press the button. Notice I'm keeping the button pressed because the engine is over the sensor, and I'm not now having multiple items added to the buffer. It's only reported as a single press. The same if I then start to add these other items, and we can see the LEDs moving appropriately. Now, using our model railway example, obviously this code would not exist. Instead, what you would do, if we imagine these trains, we'd probably have some kind of sensor on this piece of track. So we go, when this train is moving through here, when, if you like, the sensor has sensed that the train has left this section, then we would jump down, and at that point we would that's the point where, if you like, we would get rid of these lines, and it's at that point that we would next process an item in the Fifo buffer. And of course, rather than just writing some LEDs on and off, in this switch statement. Let's just bring our switch statement back. In this area here, we will probably go, okay, maybe I want a signal to be changed. I want a turnout to be changed. There could be all sorts of things that go into each of these items. If you think about the diagram we have here, if this train is the next train to go through, we might say, okay, these points have got to be changed so that it goes through. If it's this train down here, I need to change this point, and this point. So all of that would be added into the switch statement that goes in here. So that's our, if you like, our buttons and sensors example. The next example I'm going to do is reading an interrupt and working out the timings of those interrupts. So going back to the webcam, this time I have my model railway DCC controller, and here I have a circuit that allows me to read the DCC signals that are being passed from the DCC controller, and that information is then being passed to pin 2. This is an opto isolator here. That's because this system is running at what is it, 16 volts, something like that, and my Arduino will not like 16 volts. So this circuit just makes it into a signal that the Arduino can accept. Now, the reason for using the DCC controller for this is because the signals are being passed extremely quickly. So we're actually going to be measuring the interrupt time in microseconds, not milliseconds, microseconds. So this is the sketch I'm going to be using. It's actually part of a diagnostics thing I'm using for another project. So we're going to be using the interrupt pin, pin 2 on the Uno. We've then got our buffer variables. Notice this time that the FIFO buffer is an unsigned long. That is because of the value that comes out of reading the microseconds since the board started. I've then got another unsigned long variable that I'm going to use later in the code. Coming down to the setup, I'm now attaching my interrupt. It's going to be processing on the signal rising. Obviously, we're going to be using the interrupt pin 2, and it's going to be calling the function process interrupt. Now, the interrupt routine itself, this process interrupt, is a very, very short function. If ever you are processing an interrupt, the idea is, if you like, you create a pointer or something in the main loop to then do something with the information from the interrupt. If you make this line after line of code, you can have some serious issues within your program. So keep your interrupt code as short as possible. And this is a very short piece of code. So all it's doing, it's taking the value in microseconds and it is storing it in the FIFO buffer in the right position. Then we're incrementing the right position ready for the next read. So this is just getting called every time a pin starts to rise. It will put a value in microseconds into the buffer. Coming down to the main loop, I've got a unsigned long variable, my interval. And then obviously I've just got a very simple if function. Now, all this is trying to do is print out to the serial monitor the timings between the rising interrupt. That's all I'm interested in this particular sketch. So the first thing it's doing, are the read and write pointers different? If they are, that means there is work to be done. Some values have been put in that need to be processed. So what it does is it works out the interval by subtracting the latest value in microseconds from the last value in microseconds. Then, of course, in the next line, it's updating the value of last time to the current time so that it's ready for the interval to the next read that comes through. And then all it's doing is very simply printing out that interval and then incrementing the read position. Now, this sort of process is something that FIFO buffers are extremely good at, because obviously this bit of code is very simple, but I might have some code here that goes off sort of all over the place and doesn't get back to this sort of section particularly fast. Obviously, it needs to be running faster on average than the inputs, because you never want the buffer to overrun, but this could be doing some other processing, coming back to this, and if you like, it's now able to process these intervals within its own time. So let's take a look at the output on the serial monitor. Well, as you can see, I have got figures flashing away. Let's just stop that for a second so that we can see what's going on. And you can see here that I've got a time period of 38,144 microseconds. Then I've got 224, 220, 224, 220, 120, 116. And that is actually what I was hoping to see within this code. This is actually working out the difference between zeros and ones being sent from my DCC controller. But I hope this example has been useful to you, and if you've got any questions, please just stick them in the comments below the video. And don't forget, on the Digital Town site there is a whole list of resources plus all the code for this tutorial. So I hope that's been useful to you, and I'll see you in the next video. Bye for now.